Hello everyone, welcome back. So in the last lecture we introduced some preliminary ideas which will be useful. We talked about the quantum harmonic oscillator, or rather light as a harmonic oscillator, and then we talked about the field quadratures. We said, okay, these are the quantities x1 and x2 which can be used to represent the electromagnetic waves. Okay. So now in this lecture we will introduce one of the very fascinating ideas in quantum optics, that is the idea of a vacuum field. To do that, we'll have to start with the treatment of light as a quantum harmonic oscillator. We won't really go through the derivation, but we'll give you the end result. Okay, if you go through the entire theory, it turns out that the energy eigenvalues, right, of by treating light as a harmonic oscillator will turn out to be this. En is the energy eigenvalue, and then n here is the number of photons. Alright. If you look at classical electromagnetic waves, the energy can be continuously changed. Whereas quantum theory tells us that the energy is not continuously changed, but it occurs, it takes discrete values given by this quantity here. So n plus half h cross omega. Okay, this is the result of one of the important results of the quantum of treating light as a quantum harmonic oscillator. So what are the implications of this? Okay, so to understand the implications, let us first consider what are these eigenvalues that we get. So let's start with let's say we'll make the first column as number of photons, and then the classical energy, right? Classical picture, what does it give you energy, and the quantum picture, what does it give you? This is what we will compare. Let's say the number of photons in the light field is 1 photon. Classical theory tells us that the energy of that particular photon is h cross omega. But if you look at the quantum picture, it's not h cross omega, but it is n plus half, so n is equal to 1. So this will be 1.5 times h cross omega. Quantum theory differs from the classical theory. But the moment you, let's say, pick 10 photons, the classical theory tells you that the energy is 10 h cross omega, and quantum theory tells you that it is 10.5 h cross omega. And similarly, if you keep going, 10 power 3 photons if you take, you will get again 10 power 3 h cross omega, and here it will also be 10 power 3 h cross omega. Okay, so what you are seeing is, as the number of photons in the light beam increase, the quantum and the classical pictures give you essentially the same result. Okay, as n increases, classical and quantum descriptions give the same energy. And that is what we have been also emphasizing all through, right? We said that if you have a large number of photons, the classical theory is sufficient. We don't really have to do much. But the moment you go into the few photon regime, 1 photon, 3 photons and so on, then there is a divergence between the classical description and the quantum description. And that is what you are seeing, right? So to understand this and also understand the implications of it, let's again consider the quadratures that we have introduced in the previous lecture. So we said there is this x1 quadrature and x2 quadrature which are given by these expressions, correct? So, and in terms of q and p also, the generalized coordinates also, these are mentioned here. So we will use this and we will try to arrive at an uncertainty. Okay, the whole idea is that, okay, let's first compute the uncertainty in the quadrature x1. Okay, it will become clear in a moment why we are doing this. So if you consider the uncertainty, x1 is a quadrature, x1 the field quadrature, but if you take delta x1, that is uncertainty. Just like if you have a position x, there is an uncertainty in the position delta x, right? And delta p, the uncertainty principle in the case of classical mechanics, quantum mechanics, right? The Heisenberg's uncertainty principle tells you that delta x, delta p has to be greater than or equal to h cross by 2. That's the uncertainty principle. And we will see that at the end of this endeavor, we will see a similar uncertainty relation exists for field quadrature. Okay. To get that, let's go through the motion. Here, let's say delta x1. and I will use the generalized coordinates. So I'll say that this is equal to omega by 2h bar on the top. So omega 2 by h bar square, nothing more, these are constants, nothing changes, but we have to put in delta q, right? That's the uncertainty in the position in the field quadrature x1. Similarly, I can write an uncertainty relation for x2 quadrature, and that is going to be equal to 1 over 2 h bar omega whole thing under root times delta p. Okay. To arrive at an uncertainty relation, I will take the product of these two uncertainties, delta x1, delta x2. I'm taking the product of it, so I will get omega by 2h bar into 1 by 2h bar omega whole thing under root delta q and delta p. All right. So the uncertainty in the generalized coordinates, and we already talked about this. We said uncertainty in the q is essentially x by root of m, right? So this is basically going to be x into root of m. So delta x into root of m, this will be proportional to that, and p will be delta px divided by root of m. So we'll make these substitutions. Okay. So what we'll end up getting is this will be equal to those omegas cancel out and 2h cross. So we'll still retain that. So 1 over 2h bar into delta x root of m into px by root of m. And we know the uncertainty for delta x into delta p. So with that, 1 by 2h bar into h bar by 2. Right? This is greater than or equal to. Correct? So now with that, we'll see that the product of uncertainties in the field quadratures has to be greater than 1 over 4. So this is one of the important results in quantum optics. So we'll say delta x delta t should be greater than or equal to 1/4. Okay. We don't have a h bar, but the field quadratures, and also this should be valid, right? There should not be a h bar here. The reason is, remember we talked about field quadratures x1 and x2. They are dimensionless quantities. So if I have such dimensionless quantities, the product of those dimensionless quantity also should be dimensionless, and that's why it's natural that you are getting one number there, right? So is this okay? So basically we are talking, we arrived at this uncertainty relation. So what is the meaning of this? Just think for a moment, what is the meaning of uncertainty relation for field quadratures? Okay. So to understand that, we'll have to go back to our original definition of the quadratures, right? This is how we defined it. We said the uncertainty, the phasor diagram, right? Which, phasor plot of this on the quadrature axis here. We told that this vector here tells us this phasor, sorry, not vector, this phasor represents EM wave, and the length is proportional to the length of the vector, right? Or the phasor is proportional to electric field. This is what we understood. And we can represent the time variation of the phasors in this sinusoidal form. Now, we said that delta x1 times delta x2 should be greater than or equal to 1/4. What does it mean? Okay. So now let's try to understand that. So for that, let me take this axis, and this is my x1 axis and this is my x2 axis, and now there is a certain uncertainty in x1 that I'll call it as delta x1, and similarly there is an uncertainty in x2 that I'll call it as delta x2. And so in between both of them I have this point which represents my field. This phasor represents my field. Now what this is telling us is, if you assume, let's say, the uncertainties are equal, so assume if I consider both these uncertainties and they're equal, then basically the position of this phasor here is uncertain. There's a region of uncertainty associated with the phasor. So basically here the shaded region represents the uncertainty in the wave, right? EM wave, uncertainty in the EM wave. I drew it like a circle, so basically assuming delta x1 equal to delta x2. Let's assume that they're equal and they're equal to both half. With such a scenario, you will see that the vector now can be anywhere in this region. The vector need not be this, it could be this as well, or this as well. You can have multiple vectors representing the wave. And from very fundamental principles, we argued that there will be this uncertainty in this. Okay. So what does it mean? It means that this region of uncertainty in the quadratures means that the magnitude and phase of EM wave are uncertain to an extent. Okay. What does it mean? Well, we talked about this as a wave, right, in terms of quadratures. Now, instead of this, I'll end up having a wave which is probably, it looks like this, wherein I have this region. I will never know for sure what is the magnitude. There will be some region of uncertainty. This is basically magnitude and phase of wave are uncertain. That means I can't tell you that the magnitude of the wave is 1 volt per meter. I'll say that the magnitude of the wave is 1 volt plus or minus 0.2 volts per meter. There's a region of uncertainty in terms of voltage, in terms of phase as well. The magnitude and the phase. So this wave can be here, or there will be slight shift, slightly right shifted, or slightly to the left or the right. They still represent the same field with the same number of photons. So the interesting thing here is the size, the length of the phasor represents the electric field, right? So if you have a classical wave with a large electric field, then this uncertainty is going to be quite small. Okay. So if you have, let's say, classical field with large E0. If you have such a scenario, this implies this delta x1 is going to be very, very small compared to x1. Okay. So in this case, delta x1 divided by x1, if I take, and that, let's assume that both are equal, delta x1 by x2, these are much, much smaller than 1. So we don't really have to worry about the uncertainty. So if I am talking about milliwatts of laser beam and all that, I have, a large electric fields. So the quadratures are very well defined. But the moment I go to few photons, there is some amount of uncertainty that exists. And this uncertainty is critical. Okay, it essentially encapsulates the quantum nature, right? Just like when we come from classical mechanics to quantum mechanics, we say that in classical mechanics, we know the position and momentum accurately. So you can simultaneously determine the position and momentum of a particle accurately. But when you come down to the quantum regime of a few nanometers and so on, we'll say that no, we cannot determine both position and momentum with accuracy. We will, if you try to do that, if let's say you want to try to measure the position in great accuracy, then automatically the momentum is uncertain. Okay, and vice versa. So this is one of the key results of quantum theory. And we see that even if you take electromagnetic waves, if you come down to regime of few photons, this holds. Okay, and then we'll have to talk about the uncertainties in the fields. All right. And one of the very important implications of this is what is known as vacuum field. That is, I've shown you the energy eigenvalues in the past, but now if I consider what happens with n equal to 0, okay, if I look at what happens when n equal to 0, then my E is equal to h cross omega. E equal to half h cross omega, right? So that means even if you don't have any photons, there is still some E is not 0 even with no photons. Suppose you consider vacuum where there is no photon, nothing. Even there is some energy that is there, and that in the literature we call it as 0 point energy. It's called as 0 point energy. What is this 0 point energy? How much is this? Okay. For example, let's take a photon of h cross, let's say h cross omega equal to 2 eV. Let's assume that. So if I take h cross omega equal to 2 eV, you take this photon. You see that the energy of this photon is much larger than the thermal energy, right? This is kBT equal to 25 MeV, let's say. This is thermal energy, but that is much larger. The energy of the photon is much larger. So when you have such a scenario at that particular wavelength, what will be my 0 point energy? Okay. And the reason is, if you know the 0 point energy, you know that the energy, amount of energy stored in, let's say, electric field, we know what it is in terms of the energy we can find out once you know the field, or vice versa, right? So what I'll do is, I'll try to find out what is the field corresponding to this particular energy. So I'll say h cross omega is this much, 2 eV. And let me see. Okay, before I get into that, let me see. I can write half h cross omega. I'll write it in terms of the fields. Okay, so in the last lecture we derived the expression for energy and the electric field relation, right? And we also know that when you try to take the time average, the electric and magnetic field components become equal, and essentially we saw that it will become half epsilon naught E, right? E square. Let's say in this case specifically I'll write it as vacuum. Even when you have no photons, there is a certain amount of energy, and that should be this, and there should be also a volume. We are integrating over a volume. This is energy density times volume, right? So this 2 accounts for magnetic field, okay? The magnetic field contribution. So there's electric field and magnetic field contribution, so we are taking twice, okay? Maybe I'll just move it down here. Okay. So if my 0 point energy, half h cross omega, is what is the field corresponding to that, okay? And so that turns out to be equal to epsilon naught V E vacuum square. So I can find out what is my electric field corresponding to vacuum. That is h cross omega divided by 2 epsilon naught V. Yeah. So this field, basically it tells us that this expression is telling us that even when you have vacuum, there's a certain amount of electric field. That is a very different result from what you'd expect classically. When you have a classical electromagnetic field, we say, okay, there's no field, there's nothing, no electric field, right? But what we are saying is even vacuum, there are no photons, has certain amount of fluctuations, okay? So for example here, we'll compute in a moment what those fluctuations are, but this is basically called as vacuum field. Field or vacuum fluctuations. Okay, even when you don't have any photons, you have that. And in terms of the phasor plot, let's say there's no electric field, right? I mean, there is no the length of the electric field corresponds to the length of the phasor corresponds to the electric field. But in this case, when you're having no photons, effectively your phasor plot becomes like this, wherein centered at 0, you have a certain amount of uncertainty in x1 and x2. And they're both equal. There's no reason one should be bigger than the other. And that's why carefully we have chosen the quantities in such a way that this will turn out to be a circle. So this represents a vacuum state. This represents vacuum field. So there is this uncertainty that is there, even when no photons are present. All right. If not, let's try to compute what is this field and how much is it going to be. Okay. So if I, this is an example, calculate the magnitude of vacuum field in a cavity of volume 1 millimeter square at 500 nanometers. Okay. What will be the electric field consisting, if you have a large volume of 1 millimeter cube. Okay. So in this case now, if I calculate this, so A is going to be, my volume is going to be 1 millimeter cube, that is 10 power minus 9 meters cube, and my vacuum electric field is going to be root of h cross omega by 2 epsilon naught V, but 500 nanometer photon should be equal to 1.24 divided by 0.5 equal to 2.48 EV. So this is going to be 2.48 EV. EV means I write it in terms of joules. So 1.6 into 10 power minus 19 joules divided by 2 into 8.85 into 10 power minus 12 into 10 power minus 9. And if you compute this will turn out to be something like 22.5 and will nearly be equal to about 4.7 meter. If you compute this, it will turn out to be this. So when you have a large cavity of, let's say, 1 millimeter cube, you don't see really much of the field is okay. I mean, it's not really large, right? But the vacuum field is inversely proportional to cavity volume V. Okay. So now if I try to compute the same thing at let's say 1 micrometer cube, that will correspond to 10 power minus 18 meter cube, per meter cube rather. So now the calculation will turn out to be same, but h cross omega divided by 2 epsilon naught into 10 power minus 18, I'll say. And if you do all this, it will turn out to be something like of the order of 1.5 into 10 power 5 volt per meter. So you see, this is a very large field. Large electric field fluctuations when cavity volume is V is small. So this is one of the important results, because one of the, we talked about the spontaneous emission, stimulated emission and so on, right? And in spontaneous emission, we just said there is simply some, a photon which is emitted without any, reason, right? For stimulated emission, there is an incident photon that stimulates another photon to be emitted. But spontaneous emission, we said simply it will emit, right? There is no input. But one of the explanations of spontaneous emission is that it is triggered by the vacuum field. So let's say if you have a medium with, let's say electrons in the conduction band, because of the vacuum fluctuations, it emits a photon. Okay, and this you can see that the vacuum electric field is different in different wavelengths and so on. And if you have a small volume, for example, you make a nanostructure out of it, there is a large electric field fluctuations which can cause significant amount of emission into the spontaneous in the spontaneous emission, right? Large spontaneous emission, and this effectively explains why we have Purcell factor. Now we talked about Purcell factor. We said that, okay, if you have a cavity, the spontaneous emission is enhanced, and we define the Purcell factor. But an intuitive reason why this happens is that you have large vacuum electric field fluctuations if you have a small cavity, and because of that, spontaneous emission is basically very strongly, the spontaneous emission rate is very highly enhanced. Okay, and that's why we saw the fluorescence lifetimes also. The lifetime becomes very, very small when you have spontaneous emission. All right. So this is about the vacuum field, and this is one of the more important concepts in quantum optics. So I hope that you're able to understand what this is. So we started out with just to recap, we started out with the idea that, there is this quadratures that are there, and we use the results from quantum harmonic oscillator theory, and we said that energy is quantized in terms of, we can write the quantized energy for a EM wave as n plus half h cross omega, where n is the number of photons, energy eigenvalues are En, right? And we'll come back to it in the next week. But right now, if you have few photons, there is a divergence between the quantum and the classical descriptions. The energy will be slightly different. But the moment you go to large number of photons, they're nearly identical and there is no problem. The classical mechanics works. Every classical theory works very well. And we derived a relation for the uncertainty in the field quadratures. We said that there will be some uncertainty because Q and P are there. So those are related to the position and the momentum uncertainty. So we tried to relate it. And we said if you have a product of uncertainties for field quadrature x1 and x2, then you see that is at least, it has to be a minimum number of 1/4. The product of uncertainties is always greater than or equal to 1/4. And because it's dimensionless, we're getting 1/4, not h cross. Okay. Usually a lot of these uncertainty relationships have h cross. But now we don't, because we have defined x1 and x2 in such a way. If you had stuck to p and x and p, then it would be different. All right. So we did that. And then one of the conclusions of that is that the length of the phasor represents the EM wave. The length is the electric field, proportional to the electric field. Now we are saying that the uncertainty in x1 and x2 represents, or it tells us that the phasor is also uncertain. There is a certain amount of uncertainty in the magnitude and the phase of the phasor. Okay, that means that your electromagnetic wave cannot be well defined as a sine wave with, let's say, this frequency, this amplitude. There will be a certain amount of uncertainty in the amplitude and in the phase as well. Okay, so that is what this tells us. And one of the consequences of that is this idea of vacuum field, which tells us that there are some electric field fluctuations even when there is no electric field present, or there are no photons present. If I take, let's say, this volume in front of me, right, there are some very tiny fluctuations in electric field everywhere, all across space. Okay, even if there are no applied fields and so on, there is these fluctuations that are present, and that is the consequence of the quantum theory. Okay, and now those things, if you look at it, if you compute how much is a vacuum field, you will see that if you take a small volume, right, 1 micrometer cube is not really a very large volume. I mean, we have plasmonic cavities with even smaller volumes, right? It turns out that the vacuum field is quite significant, and it can actually lead to very strong enhancement of the decay rate from excited dyes or molecules and so on. So these things, this large vacuum electric field can explain the Purcell effect, and also it's central to a lot of different aspects of quantum mechanics. And that's what we did. So with that, I would like to stop this lecture, and then we'll meet in the next lecture. All right. Thank you so much.